Literally scores of barrier materials have been produced over the years to package everything from diodes to jet engines. And the sole reason is to safeguard military supplies for transportation and long-term storage under all types of climates. But a barrier, no matter how good it is, can be no better than its seal. Thus, a bad seal is worthless, but a good seal will prevent damaged materials, the loss of thousands of dollars, and possibly the immobilization of mechanized units that did not get needed and usable replacement parts. Most workers in military packaging are very aware of these facts and accept them. But there are a few nonconformists. Clarence here is a good example. For the most part, he's a good worker. But there was a time when he'd never take anybody's word for anything, had to prove everything to himself. So, naturally, he did a lot of thinking and a lot of worrying. No, it wasn't a matter of peanuts. They just helped to trigger things. You see, he was at the packaging end and not the receiving end, so he was a bundle of questions. Did his packs arrive in good condition? How good were the seals and the barriers? How could he really tell if a barrier was grease-proof, or waterproof, or water vapor-proof? Well, the truth is that every barrier is made to do a specific job, and every one is tough. Opaque barriers, for example, are usually made of more than one layer to form a multiply sheet. The face, which is heat sealable, is made of thermoplastic. The impervious ply, usually metal foil or plastic film, provides grease-proof, waterproof, or water vapor-proof properties. The backing sheet may be plastic, cotton cloth, or craft paper. The craft is sometimes reinforced with glass fibers or other materials. The heat-sealable face also serves to fill tiny pinholes in the underlying plies to aid in making the barrier resistant to water, grease, or water vapor. Transparent or unsupported plastic films also provide grease-proof, waterproof, or water vapor-proof protection, depending upon the properties of the film. Sure, Clarence was given all that information, but did he accept it? No. Nor did he believe that most heat-sealable barriers used by the military today will have information on the backing ply, stating the sealing requirements for dwell time, pressure, and temperature. If not, the sealing information will be on a slip sheet. Fine, but just try to convince a non-believer. Anyhow, as the story goes, Clarence finally hit on a surefire way to prove things to himself. And it all hinged on that old watch of his. A clunker that had seen much, much better days. The idea, of course, was to slip that old watch in a bag, seal it up, and hang it outside the house. Sure, to test the packaging. And that's just how he explained it all to the boss when he appeared from nowhere. But the boss had another idea. Why not hang it up outside the plant entrance for a while, Clarence, where we can all check it, the boss says. Well, he was the boss. So that's where the watch went, outside the building entrance, where everybody could see it. And so it hung there for quite a spell, through hot sun, rain, sleet, snow, whatever. As the weeks went by, that old watch not only gained a lot of attention, it raised quite a few questions. Would the barrier hold up? Was it the right barrier? Was it a good heat seal? Had Clarence been careful about the right temperature, dwell time, and pressure? Finally came the moment of truth. All those questions would be answered one way or another. No, the watch didn't fare too well. But according to the boss, there was nothing wrong with the barrier. It had to be the seal. The rusty watch was proof of that, no doubt about it. Fortunately, nobody lost out by the experiment. They learned something about barriers and seals firsthand, especially Clarence. He actually proved to himself that poor heat seals can quickly harm a packaged item. that poor heat seals are always the result of improper correlation of temperature, dwell time, and pressure. As Clarence learned, and every experienced operator knows, enough heat must be applied to the thermoplastic material on the sheets to be bonded, so it will soften and reach its flow temperature. Too low a temperature may result in either no seal being made or at best a weak seal. Too high a temperature may cause delamination or separation of the backing ply and/or decomposition of the thermoplastic. Barrier materials must be capable of being heat sealed at a temperature no higher than 525 degrees Fahrenheit. And dwell time, the length of time the barrier material remains in the heating zone, must be sufficient to raise the temperature of the heat sealable face to its flow temperature so the molten thermoplastic surfaces will form one continuous mass. Since dwell time and temperature are interdependent, the lower the temperature, the greater the dwell time must be, and vice versa. Pressure, the third essential for a good heat seal, is needed to bring the surfaces to be sealed into close and continuous contact, so the heat will flow through the backing material to the thermoplastic surfaces. Too much pressure tends to force the molten thermoplastic material out and cause defective seals. 40 to 80 psi is the pressure range that should be maintained. There are two types of heat sealers in general use by the military today: the continuous type and the unit or jaw type. Though they may have many variations or attachments depending on the make, their basic operation is essentially the same. The unit or jaw type sealer has two opposed parallel jaws which can be brought together either by hand or mechanically. Heating elements may be provided in one or both of the jaws. Temperature is controlled by a thermostat. Dwell time is controlled by the duration of pressure, either manually or by automatic timing devices. Pressure is controlled by a spring or a pressure cylinder which is powered pneumatically or hydraulically. The continuous type sealer is available in two basic variations: the rotary and the band type. Both are used for high volume work. In their simplest form, rotary sealers consist of a pair of driven and heated rollers through which the material to be sealed is passed. Dwell time is controlled by varying the rate of speed at which the material passes through the rollers. The rotating wheels are used to apply heat and pressure to the barrier material to effect a seal. Temperature is accurately controlled by a thermostat. In addition, some rotary sealers also utilize preheaters to raise the temperature of the thermoplastic before sealing. A pressure control determines and measures effective sealing pressure. Rotary sealers are usually equipped with a chain or belt drive intake to feed the material into the sealer and a discharge unit to guide it out. The band-type continuous sealers make use of two thin, endless metal belts to carry the material through the heating zone, and sometimes a cooling zone, while applying pressure and heat continuously to the barrier. The band type operates by transferring heat from the jaws through the metal bands to the barrier material. Dwell time is controlled by varying the speed of the bands through the heating zone. Temperature is thermostatically controlled. And pressure is usually applied by rollers, although the heating jaws also apply a small amount of pressure to the bands. Roller pressure is controlled by mechanical and/or hydraulic power. Continuous type sealers for unsupported plastic film are also available. In addition to the heated zone, they use a water-cooled zone so the unsupported film will not melt and fuse onto the steel belt. The thermal impulse type heat sealer is also used primarily for sealing unsupported films. It looks and operates much like a conventional unit or jaw type sealer, except that an electrical resistance wire is mounted on the sealing jaw. The wire, when brought in contact with the material, is heated in a fraction of a second by a heavy current flow to melt and fuse the thermoplastic. The jaws remain closed after the flow of current to cool the seal under pressure. The 4 controls located on top of the machine consist of the dwell control, the recycle control for making single or multiple seals, the on-off switch, and the heat control. An entirely automatic thermal impulse type heat sealer, which requires only minimal attention, is ideal for use in long packaging runs involving small items of a like nature. Before any runs are made, of course, temperature, dwell time, and pressure controls must be properly set for the material being sealed. But even with the best equipment and materials at hand, it's essential to follow the manufacturer's recommendations for operating and maintenance procedures to achieve good heat seals consistently. This means each machine must be checked regularly to be sure it's free of grease or other foreign matter, free of defective or worn parts, and operating efficiently. To assure correct temperature control, a pyrometer should be used daily to check the temperature of the heat sealing surfaces. The temperature indicators should then be adjusted accordingly if necessary, so they will reflect the true temperature of the unit. As a starting point for making good heat seals, always check the manufacturer's slip sheet that's provided with each roll of barrier material. These sheets provide recommended temperature, dwell time, and pressure to be used on rotary, band, and jaw type equipment. The information is excellent for making a trial heat seal, but beyond that, it should be used cautiously, since some thermoplastics and adhesives change characteristics upon aging. The manufacturer's recommendations might also be for a type of sealer which may differ from the one you are using. If the manufacturer's recommendations do not result in a good heat seal, or they are not available, correct settings may be established by a series of trial and adjustment settings made at increasing temperatures, which dwell time and pressure are kept constant. Dwell time is set at 2 seconds. Temperature settings should start at about 250 degrees Fahrenheit and pressure at 60 psi. The barrier material samples are placed in face-to-face contact as test specimens. Each specimen is then sealed at 25 to 50 degree increments of increasing temperature. After cooling the sealed specimens to room temperature, each one should be pulled apart. The correct temperature to use is the lowest one at which the heat sealable layer pulls completely away from the other plies of the barrier material. Any color change on the heat-sealed area of the backing material are sure signs of too much heat. Final proof of a good heat seal, of course, is its ability to pass the test set forth in the specs MIL P116, not its ability to protect an old watch. Incidentally, the better operators like Clarence test their seals frequently, because they've learned that no machine will run indefinitely without adjustment, and no barrier materials will be completely uniform. A good operator also feeds the material into the sealer, so both faces are free of wrinkles and puckers. This prevents channeling in the seam, which could cause leakage. Any excess air that might be in the package can be squeezed out by hand before the package is completely sealed. Excess air can also be removed mechanically, but when using a device, never remove all the air, because the barrier might then come in too close contact with the item and result in possible damage to the barrier. Any handling which puts a strain on freshly made seals before they have cooled should be avoided. When opaque bags are made up for sealing purposes, all 4 sides must be sealed. Likewise, whenever bags must be cut to smaller sizes, they should be made no larger than necessary so they can best conform to the material. The packaging of outsize items also calls for special treatment. Barrier materials must be carefully cut to proper size to fit the item. Then, hand sealers must be used with the same attention paid to temperature, dwell time, and pressure as in other sealing jobs. When heat seals are made on equipment designed to control temperature, dwell time, and pressure, samples should be obtained from sealed packages or prepared from specimen heat seals for testing. When specimen heat seals are prepared, they should be made up daily prior to production from samples of each barrier material sealed on each sealing device. Machine settings used in production must be identical with those used in fabricating the test specimens. The heat-sealed seam strength test must always be done according to established standards, preferably at room temperature and with static load weights as specified. If the temperature in the test area exceeds 90 degrees Fahrenheit, a 5% reduction in the static load is permitted. Partial separation of the seal is acceptable within the first 2 minutes of the test, but any separation of the heat-sealed area during the final 3 minutes of the test is cause for rejection. To be effective and do its intended job, the heat seal should be just as strong as the barrier material itself. And this test, which meets the heat seal test requirements, is quick, it's reliable, and it guarantees a good package for storage or transit. And again, you don't even need an old watch.